Welcome back. Today's goal of this lecture, today I will see at first differentiability of functional several variable. In my previous video I had discussed differentiability of functional several variable. Actually today I will see what is the Jacobian matrix total differentiability. In my previous video I had discussed this is also, but today I will see this part as a review and I will see what is the relation between differentiability and directional derivative, what is the total derivative and what is the Jacobian, what is the relation between total derivative and Jacobian matrix. Okay, this is the today's goal of this lecture. Also I will see some example which had come in different type of competitive exam. I will see this type of example first content, but before that please subscribe my channel and click the bell icon so that you will get all notification of my new video. Okay, let's see the first question. Today at first I will see differentiability of functional several variable, total derivative in function. In function define real line to real line, we all of us know derivative is if C be interior point of real line, derivative at the point C is f prime C equal to limit h tends to 0 f of C plus h minus f of C divided by h, where h belongs to R. In functional several variable we can define it as same way. Then the error term is defined as ECH equal to f of C plus h minus f of C divided by h minus f prime C. Then limit h goes to 0, ECH is equal to limit h goes to 0, f of C plus h minus f of C divided by h minus f prime C. Okay, and this means actually f prime C, that means f prime C minus f prime C, that means this is equal to 0. Therefore limit h goes to 0, ECH tends to 0. Therefore we can write this as f of C plus h equal to f of C plus h f prime C plus h ECH, where limit h goes to 0, ECH equal to 0. Okay, now define a map TC from R to R such that TCH equal to H f prime C. Clearly this TC is a linear transformation. And TC is uniquely determined by f dash C. This TC is called derivative of f at the point C. So several variable, if f defined from S, where S subset of Rn to Rm be a function and C is a interior point of the set S, then the function f is said to be differentiable at C if there exists a linear transformation T such that TC equal to, which is defined from Rn to Rm, such that f of c plus v equal to f of c plus TCV plus norm v is ECV, and this is actually error term. In my previous video I had seen this is elaborately, and limit a is goes to 0, ECV equal to 0, and this TC is called the total derivative of the function f at the point C. There exists a linear transformation, so we all of us know from a linear transformation we always get a Jacobian matrix, because for a linear transformation we can generate one matrix, and this matrix is called Jacobian matrix here. In this expression, if v equal to ASU, if we put v equal to ASU, then this would be f of c plus ASU equal to f of c plus TC ASU plus norm ASU EC ASU. Then we can write this as f of c plus ASU minus f of c divided by AS equal to TC ASU divided by AS plus norm ASU divided by AS EC ASU. And if we take limit AS tends to 0 both sides, then these would be, if AS goes to 0, then limit AS tends to 0 f of c plus ASU minus f of c divided by AS equal to limit AS goes to 0 TC AS plus limit norm ASU divided by norm AS EC ASU, and limit AS goes to 0, this part is goes to 0, that means limit AS goes to 0 f of c plus ASU minus f of c divided by AS equal to limit AS goes to 0 TCS. Sorry, TCU. And this is called the directional derivative of f at c in the direction u. That means total derivative exists means all directional derivative exist. That means total derivative exist means all directional derivative exist, and value of f at c in the direction u is actually the image of u under the linear transformation TC, where f prime cu equal to TCU. That means this is actually a directional derivative of f at c in the direction u. Okay, and that means let f from s, which is defined from Rn to Rm, is differentiable at the differentiable of the function f at c. That means derivative is equal to Tc or f dash c, and this Tc or f dash c is actually the linear transformation from Rn to Rm, and this Tc or f dash c is called Jacobian matrix. Why? Let U1, E2, En be the standard basis of Rn, then Tc E1 equal to f prime c E1, which is equal to D1 Fc, which is equal to D1 F1c, D1 F2c up to D1 Fmc. Similarly, Tc E2 equal to D2 Fc, which is equal to D2 F1c, D2 F2c, D2 Fmc. Similarly, Tc En equal to Dn Fc, which is equal to Dn F1c, Dn F2c, Dn Fmc. Therefore, we can write this matrix as DFC equal to d1 f1c, d2 f1c up to dn f1c. Also this is d1 f2c, d2 f2c up to dn fnc. This would be continue d1 fmc, d2 f2c up to d2 fmc up to dn fmc, and this matrix is called the Jacobian matrix. Directional derivative f at c in the direction u by f prime cu or duc, and the Jacobian matrix f at c equal to dfc. Therefore, f prime cu equal to tcu, which is equal to u1 d1 fc up to un dn fc. Since there are f1, f2, fm component, so f prime cu equal to actually u1 d1 f1c, d2 f2c up to dn fmc. Similarly, un d1 f1c, d2 f2c up to dn fmc. Okay, that means from this expression we can write this as, d1 f1c up to dn f1c. This would be continue d1 fmc up to dn fmc times u1 u2 up to un, and this is equal to actually f prime cu equal to dfc u1 u2 up to un, and this is equal to dfc u. I hope my all viewers have understood this is. The kth row of the Jacobian matrix is actually the gradient vector of fk, and d of fc equal to d1 f1c up to dn fnc. This would be continued d1 fmc up to dn fmc, which is equal to gradient of f1c up to gradient of fnc. So, directional derivative of the function f of c with u equal to f prime cu, which is equal to gradient of f1c up to gradient of fnc dotted with, this would be actually dot product of u1 u2 up to un. I hope my all viewers have understood these rules. Okay. Well, next, we all of us know if the partial derivative is continuous, that means f belongs to c1. c1 means if fx and fy means c1 means actually all partial derivatives are continuous on the set A subset of Rm, then f is differentiable on the set A. But this continuous partial derivative at a point A or at a neighborhood of A, this is sufficient condition, not necessary condition. Continuous partial derivative at a point A is not necessary condition for differentiability of a function at a point A. If the function has a partial derivative and if the partial derivative are continuous at a neighborhood of a point, then we can tell function is differentiable at this point. but there is more function where function is differentiable but partial derivative are not continuous. Let's see one example. F who is be defined from R2 to R such that f of xy equal to modulus mod xy. Show that f is differentiable at the point 0, 0. That means we have to prove there exists Jacobian matrix such that f of 0, 0 plus a is k minus f of 0, 0, if minus, consider the Jacobian matrix A is k divided by norm A is k, this expression tends to 0 as A is k tends to 0. We have to prove this. Partial derivative, at first we have to find the A. Partial derivative with respect to f at the point 0 is f prime 0 e, which is equal to limit t goes to 0 f of 0 plus t e1 comma 0 minus f of 0, 0 divided by t, and this value is limit t goes to 0 f of t comma 0 minus f of 0, 0 divided by t. If you put f of t 0, this would be 0, so this value would be 0. Similarly, d2 f0 equal to 0. That means the set A is actually 0 comma 0. Therefore, if we put here, then I will get value would be f of A is k divided by norm A is k, and f of A is k means modulus of A is k divided by norm of A is k, and modulus of A is k, this is less than equal to mod A is times mod k, and this is less than equal to norm A is k times norm A is k. Just put the value here. This is less than equal to norm A is k times norm A is k divided by norm A is k. That means this is less than equal to norm A is k. And as A is k tends to 0, this value tends to 0. That means limit A is tends to 0, k tends to 0, this value goes to 0. So, f is differentiable at the point 0, 0. At the point 0. Okay. Next, consider xy not equal to 0. Then partial derivative of f of xy is limit t goes to 0 f of xy plus t10 minus f of xy divided by t, and this value would be limit t goes to 0 absolute value of x plus t times t minus f of xy means absolute value of xy divided by t. When x equal to 0 but y not equal to 0, then I will get, this means limit t goes to 0 absolute value of x plus t times t means absolute value of x plus t times absolute value of t minus xy divided by t. If you put x equal to 0 but y not equal to 0, then I will get, sorry, this would be y. Here x plus t and this would be y. Here y. Just here means, this means mod of x times mod of y. This means. So just common mod of y both side. Then this would be limit t goes to 0 mod of x plus t minus mod of x divided by t. Since x equal to 0 I have considered, that means this value is mod y limit t goes to 0 mod t divided by t, and this limiting value does not exist. So d1 f of xy for any is not defined for any neighborhood of the origin. d1, because x equal to 0, y not equal to 0, this is the neighborhood of 0, 0. So d1 f of xy is not defined for any NBD of origin, but f is differentiable. Here f is not C1 but f is differentiable. I hope my all viewers have understood. When C1 function, then always f is differentiable, but differentiable this does not always imply f is C1. Okay? OL.